Okay, so I want to start out with the kind of a proof that I showed some of you guys already in class, a few of you, but okay, so I want to first say that the limit as x approaches a, if you plug in and you get 0 over 0, this is actually the same as infinity over infinity. Okay, so suppose that this one is infinity, that these both are. So the limit as x approaches a of f equals the limit as x approaches a of g equals infinity. Then the limit as x approaches a of 1 over f is the limit as x approaches a of 1 over g. And these things are getting infinitely large, so 1 over them is going to 0. And this is, you could pick any constant you want, actually, right? And because f of x over g of x equals 1 over g of x over 1 over f of x, just invert and multiply and your f ends up back on top. Then if this was 0 over 0, then this is infinity over infinity, plus or minus. And if this one is infinity over infinity, then this one is 0 over 0. Okay, but they're equal. So these indeterminate forms are actually the same guy. So for the proof of L'Hopital's rule, which applies only when you get 0 over 0 or infinity over infinity, if these are what you get when you straight take the limits to start with, then suppose f and g are differentiable at a, where we're taking the limit as x goes to a. Then that also means they're continuous, so I'm going to use that later. So I want to look at the limit as x goes to a of f over g. Okay? That equals the limit as x goes to a of the limit as h goes to 0 of f of x plus h over the limit as h goes to 0 of g of x plus h. And then I'm just going to multiply by 1 over h over 1 over h. Okay, now I'm going to subtract. I forgot to write my other suppose. Suppose further that f of a equals g of a equals 0. So when I first take this limit, I get 0 over 0. But now I'm going to use that fact, and I'm just going to take a minus f of a right there and a minus g of a right there. These are 0. I'm subtracting 0 here and I'm subtracting 0 there. So it doesn't matter. So I'm depending on this 0. Now I'm going to use continuity again. So this is the limit as x approaches a of f of x plus h minus f of x over h, because I have this limit out here, so I'm going to end up with f of a when I plug in, right? G of x plus h minus g of x, only I forgot to write my limits. Okay, so I'm letting h go to 0, which means that this part's going to f of a still, but this f of x over here is not being affected by these limits, right? F of x and g of x don't have an h anywhere. So this limit doesn't affect them, but this outside limit does. So that's a replacement for f of a, g of a. So this equals the limit as x goes to a, f prime over g prime. So what this says is if you get 0 over 0 or infinity over infinity, you can just take the derivatives on top and bottom. So don't apply the quotient rule, just take the derivative of the top, derivative of the bottom. And then if you still get 0 over 0 or infinity over infinity, do it again. And you keep doing it until you either get 0 over a number that's not 0, at which point your limit's 0, or you get a number over 0, at which point your limit is infinite. So if I take these, that first one, the first thing you always do is plug in. So we plug in 1, and we get 2/5. So that's a finite standing number, and we stop. This one, if I plug in 1, I get 0 over 0. So the thing that we've done in the past is factored. So x squared minus 1 is x minus 1x plus 1. So we cancel this out, and now we plug in again. And then this one, we've done the Bogobot needs DC, but let's just assume not. So we have this x squared minus 1 over 2x squared minus 1. And then we would have to do the 1 over x squared, 1 over x squared, because remember the official rule was dividing by the highest power of x. So then we get 1 minus 1 over x squared, 2 minus 1 over x squared, and then these go to 0 so that we get 1/2. So that's how we did them before. So that's a little reminder. That's way back at the beginning. Okay, so now we get L'Hopital's rule. There. Now we're going to look at these.
Exclusive acoustic versions of well-known songs. She doesn't know.
Okay, so for this one, step 1, always plug in. So 2 squared minus 4 over 2 minus 2. That was super weird. 0 over 0, so we can't do it. So we take the limit as x goes to 2, differentiate, differentiate. Plug in again, done. So in the past we would have factored x minus 2, x plus 2, we would have gotten the x plus 2, and then we would have gotten the 4. So as evidence that it works. Okay, so I try natural log 0 over, oh sorry, getting ahead of myself again, natural log 1 over 1 minus 1. Natural log 1 is 0, so 0 over 0. So limit x goes to 1, take the derivative, plug in again, plug in 0, you get 1 minus 1 over 0. Derivative, derivative. Well, I don't think I can get those 3 at one time. So. Okay, so that first one, as x goes to infinity, that goes to infinity. Either the x gets arbitrarily large as x gets arbitrarily large, so does x squared. So we get infinity over infinity, which means I can apply L'Hopital's rule. I still get infinity over infinity. This time I get infinity over 2. So it's infinity. Basically, e to the x grows faster than x squared. You should probably know that because you're always hearing the phrase, that grows exponentially, even when it's a lie. Anyway, exponentially is very, very fast. Okay, so this one, plug in infinity and over infinity. Now you know by Boba Bot needs TC that this ought to come out 2/3. So you get infinity over infinity again, so okay, so if I plug in 0, that's a bunch of zeros, that's a bunch of zeros, so I get 0 over 0. I'm going to take the derivative. Okay, so this time if I plug in 0, I get 0 on the top, but I don't get 0 on the bottom. So part of you wants to keep on going, especially after seeing those infinite ones, but you can't. This is 0. Okay, so the limit is actually 0. This one I plug in 0, I get 0 over 0. So I plug in 0 again, I get 0 on the top, and I get 1 on the bottom. So again, 0. There we go. Okay, so I plug in 0, and I get square root of 9, so 3 minus 3 is 0. And then down here I also get 0. So I take the derivatives. This is 9 plus x to the 1/2. Plug in 0 again. And this certainly is not 0 over 0, so it's 1 over 2 times square root of 9. Pretty handy little tool here. Okay, and then the last one asks what's wrong with this. So I plug in 0, and I get 0 squared over 0 squared plus 3. That's 0 over 3. And remember when I was doing the proof that I depended completely on continuity, differentiability, and those values being 0 at the point. So if you don't get 0 over 0, then that whole proof falls apart and you can't then take the derivatives. Okay, so that wraps us up, I guess.